All right. This is a bit of an escapee from a developer day talk, so I'm sorry in advance if it ends up a little more sort of file system internals and stuff. Hopefully it'll be interesting. I want to stress, this is all about stuff that's already done. So this is new work that's released in 2.11. So this is about improving performance for small I/O with Lustre, which has historically been a pain point. So, small I/O is really bad. It's a distinct problem from small files. You often get the two together, but it's worth distinguishing, as we'll see here. It's very hard to give good performance with small I/O, just all sorts of reasons. It's also important to define what you mean by small. Some people think small is 8 bytes. Some people think small is 1 meg. So it does vary. For the purposes of this discussion, we're going to talk mostly about really small stuff, which is useful because, in general, performance degrades more or less consistently as you go smaller. Again, there are a few different boundaries you cross. Particularly interesting one, as we'll see here, is 1 page. And we're all going to assume page sizes are 4K because, x86 is the only architecture there has ever been or will ever be. So why is small I/O so bad? What we're going to talk about mostly here is client-side stuff, and it's probably the main reason why it's bad. So it's per I/O overhead. It's much worse on a big file system like Lustre than it is on a local file system. There's a lot of work you do regardless of the I/O size. You've got to do locking and cache management and maybe stuff to make sure you're not out of space, all sorts of different things, tracking the file size, all sorts of different stuff, and it adds up. And then there's also, if you actually end up doing I/O over the network, there's network costs per I/O, sort of various overheads there. And there's not really any obvious pain points. There aren't any flame graphs in here because they're kind of boring. You see Lustre's been optimized some. If you look at sort of where it spends its time when it's doing I/O, well, it's a lot of different places because it's got a lot of different things to do. If there were a real hotspot, I probably have leaned on it and would be talking about that instead. So one other thing to highlight, of course, is if you're doing small I/O, is that spinning disk has historically been a big problem. The driver for this work was actually looking at trying to use flash better, and yet people expect that flash will be better with small I/O, so we thought we'd take a look at it. So what do we do today to improve small I/O in Lustre? We reuse the LDLM locks. LDLM is the Lustre Distributed Lock Manager. That's the locks that provide your basic consistency guarantees between your clients. It's the network level locking between clients and servers. So most of the time when you do I/O to a file, you've already done I/O to the same file. Most I/Os are not the first one, and so unless you're dealing with conflicts, you will already have the lock for that, so you can avoid the round trip to get the lock. That's hugely helpful. If you don't do it, it has enormous costs. So for sequential small I/O, we do read-ahead and we do write aggregation. So both of those allow you to avoid doing small I/O over the network and to the disk, but you still have to process them on the client. And as we'll see here, that can still be pretty painful. So if the user space provides an 8-byte I/O, there's a lot of work you still have to do that's the same as if user space provided a 1 megabyte I/O. Very painful. So, and then about random small I/O, it's not the best story here. You can sometimes do direct I/O, although it's worth noting that random and page aligned, which is required for direct I/O, don't often go together. In fact, very often not. So we just sort of tell people don't do it. Definitely we spend a certain amount of time on libraries and also just cajoling user applications to avoid doing small random I/O. A little more in-depth on reads. So read-ahead, that's something probably all familiar with. Just use the page cache. You recognize, well, you read this, you're probably going to read the next thing. So even though you only read a page or two, you also read a page or two a moment ago, so I'm going to read 2 megabytes or 4 megabytes or 16 megabytes. It guarantees you do large I/O over the network and down to the disk, but again, it doesn't fix the per I/O overhead for small reads. So there's some new tricks in this area, some of which have already been mentioned, and they kind of come down to do read-ahead better and do it more often. So fast reads is more about doing it better. I'll get into that in depth. That's a feature from Andrew Parpeshko, now at Cray, and Jinshan Shung of Intel. So, well, sorry, for Uber, excuse me, recent changes. There's also a proposal to do Lustre's read-ahead fully asynchronous. It's semi-asynchronous now, as Jinshan would probably remind me if he were up here. But it could be made more asynchronous, and that's proved tough. There's some competing proposals in that area. If you're really interested, please weigh in. one more thing we're going to talk about is partial page read-ahead, which we'll get into shortly. So before we get to partial page read-ahead, we have to explain what it is and why it matters. So this is about overwriting files. This is something, it's a use case that comes up, and it's very bad when it does. So overwriting an existing file in Lustre or any other file system seems a lot like writing a new file, seems like it should be the same, and it is, except if it's not aligned. Because if it's not aligned, then you have to start reading things in from disk. If you write part of a page, the Linux page cache says, no, I need the rest of the page. I need to have a full page. So if you write the first 8 bytes of a page that already exists on disk, you have to read in the rest of the page before you can do it. So just as an example here of the cost of that in Lustre, at least prior to 2.11, if you're doing I/O at 4,096 bytes, so one page, you get 600 megabytes a second for a new file, 600 megabytes a second for overwriting. And if you do 4,097 bytes, it's so unaligned, but only slightly. It's a tiny bit worse for new files. And for overwrites, suddenly it's 3% of the performance you had before. You see the same sort of thing at slightly larger sizes. Eventually, as you go up, the overhead goes away, but it's pretty serious. So when you're preparing these partial pages, I write 4,097 bytes. I write the first page, the 4,096. Everything it just writes. It's fine. It's easy. To write the one additional byte, I then have to read a page off of disk, which means I have to go all the way to the server, get it, bring it in, load it in, and then I can write my byte into it. It's very, very inefficient, but there's no way to avoid it, at least without more knowledge of the application's behavior than you usually have. So we do have a solution for reading pages in one at a time using Readahead. And so, but we don't historically, mostly because, frankly, nobody had really worried about it. It turns out it's pretty easy to do. There's another subtlety here that makes this a little more interesting, which is if you have multiple writers writing to the same file, the file size will be, large areas of the file will be empty because they'll be writing to different extents of the file. And what that can mean is they will read in data that does not exist. So if one writer is trailing another, the first writer will read up data that the second writer has not actually written, but it believes is there because the file size is down there. So solution to this, we call it partial page read-ahead. It's from myself and Jinshan. And just that's the same graph again with partial page read-ahead, which is, again, basically just using read-ahead so you can read in more than one page at once when you're bringing them in this manner. You get up to 70%. Remember, that was 3% before. So quick graph. This one's a little more complicated. So you've got the new file, the overwrite with partial page. So that's all straightforward. The shared file is a little different. You can't show the shared file in the ideal case because it doesn't exist. But if you were doing 1K writes of a shared file from 4 writers, you get about 50 megabytes a second on my test system. And one thing real quick, I wouldn't take any of these specific numbers as gospel. Look at ratios, right? Some of this is in VM, some of it's on hardware, and all of this will vary depending on your setup. So think about ratios. The ratios should be consistent. But we get 50 megabytes a second without it, and with it, we get 500 or so. So 10x improvement. The other ones were more like 20 or 30. So it's somewhat of a narrow case, but it's a big improvement. So this is stepping back a little bit. Fast reads. This is not. I want to stress this is not my work. It's just something that we need to talk about to get to some of the stuff that I've done. So Readahead brings in pages before they're needed, which means that most user space reads are satisfied from cache. So even if user space is reading a megabyte at a time, most of those 1 megabyte reads never hit the server directly. They're handled by something that was read in already. And then maybe they tickle Readahead and you get some more data further down. But the point is, most user space reads do not actually themselves generate a read to the server, even if they're relatively large. And if they're small, almost none of them do. So the normal older read code does a lot of work to check the locking for cached pages. It goes and makes sure everything is happy, checks all the Lustre stuff, checks the network locking, just make sure everything is safe. But the thing is, Lustre already evicts pages if somebody else tries to write to them, or if various other events happen. And so that means is we can assume that any page that's found in the page cache is safe to read. And so what that means is we don't really have to use Lustre to read them at all. We can essentially go directly to the page cache. If a page is present and it's not dirty or whatever, then it's fine. We can use it. We don't need to ask Lustre. We don't need to check to make sure that it's locked correctly, because we know, because of the other guarantees that Lustre provides, that if it's present, it's fine, and if it's not fine, it's not present. So this is really fast. I don't remember exactly when this landed. We got it in from Intel's 2.7 FE, but I'll show a few graphs here. So this is without fast read and with fast read. You can see it's several times for all these sizes. So that's bytes on the bottom. So, you know, at 1K, you're looking at like a 5x improvement. You know, at 4K, you're looking at, you know, again, like a 3 or 4x improvement. And even up at 1 meg, you're looking at a 2 to 3x improvement. And I'm going to zoom in on the small part of the graph because you can't see how big those differences are. This is 8, 16, 32, 64, with and without. All of those are about a factor of 20. It's worth having. So basically, again, if user space is doing small sequential reads, it'll now go 20 times faster than it would a few years ago if you're running anything fairly recent. And so this is the inspiration for some other work. So this is about writes. So what about writes? Can we do the same kind of trick for writes? Well, okay, so what are this page cache trick? So what's the state of the page cache when you start writing? Well, the answer is it's empty. Why would there be anything in the page cache? You're writing. This is new. You're creating it. You could imagine a case where you were overwriting a page that already existed, but that would basically mean that you had dirtied a file and now you were writing it again. It's not very likely. So, and writes are intrinsically more complicated than reads. They're modifying the file. They modify the file size. You have to track things so you don't run out of space. You have to make sure you write the dirty pages back. You can't just drop them in the page cache and then forget they exist until something forces you to deal with them. There's more you have to do. So if there were a dirty page to be present in the page cache already when we got there to try to write to a portion of the file, then we know that most of this is handled. There's space for the page is allocated, somebody cares about the fact that it's dirty, so they'll write it out. Yeah, okay, so these things are true, but so what? Dirty pages aren't present until we write to them. There's one useful exception to this. It's not even really an exception, it's more just a special case. If you write a few bytes at a time, say 8 bytes again, the first 8-byte write will create a dirty page. And all of the locking and allocation and space tracking and dirty page tracking will already be done. And that's the same work that would be done if you'd written 4K. And in some of it's the same work that would be done if you'd written 1 meg. But the thing is, if we then proceed to write 8 bytes again, well, there is a dirty page. Well, probably. I mean, there might not necessarily be. It could have been flushed or something. But assuming it hasn't been flushed, there is a dirty page. So a user writing 8 bytes, 8 bytes, 8 bytes, which is terrible, but people do, they will run into an already present dirty page. And so the idea is here called tiny writes. When a write is less than 1 page in size and the page is already dirty, you can write directly to the page, meaning, again, you can skip all those complicated Lustre processes and basically just drop your I/O in the page. It's a new feature in 2.11. This was also a little hard to show on a graph because of just the size ranges, but we've got the linear column is a little confusing. That's if Lustre scaled linearly from 4K according to size. So just, you know, multiples of size. We already do a little better. You can see 8 bytes is 2.3. It's about double what you'd expect if we were just linear with regards to I/O size. But then if you look with tiny writes versus 2.3 is what we do today, 12. So, you know, it's about a 5x improvement if you're writing 8 bytes at a time. More like 4.5 if you're doing 64. And it's only about 50% at 1K. And at 4K and up, it does absolutely nothing because you can't use this facility anymore. So as a graph, it's basically the same information. I said I don't think that's too illuminating. And because 4K is frankly so much faster, it doesn't really fit on the graph. The rest of it all ends up squished down at the bottom. So that's why 4K is off this graph. So, but it's a pretty decent improvement. A little bit more about other stuff that we'd like to do in the future. So tiny writes are obviously very limited in applicability. If you've got a well-behaved application that's doing good I/O, it's never going to see this feature. Won't be able to make any use of it all, won't help you at all. So can we do any better? And Jinshan had a proposal, which is actually sort of, in some ways, tiny writes is a derivative of it, something that he called write containers. Now, unfortunately, Andreas has borrowed the name write containers for something else, so maybe we need a new name. But the idea is that you would prepare a lot of the per IO items in advance, and you might you would imagine a bucket or a container, and when you do an IO, you would create a bucket, maybe a few megabytes in size or something. The bucket would hold the reference on the lock and everything else and make sure that the locking properties and other things required were followed. And then also, because you're doing this larger size, you could do things like allocate pages in batch mode and things like that, all of which are can be much faster. And that would mean then that essentially you could, again, not too dissimilar to tiny writes, just sort of drop I/O into this pre-existing bucket. You just have to create this nice big bucket. Design only. I've described a significant portion of the design. Jinshan would like volunteers. He sort of wishes I'd volunteer. I don't have time. So if somebody else is interested, he or I would, I'm sure, be happy to help with design and implementation and review. I'd expect a performance boost of several X for small I/O, and potentially, I wouldn't be surprised if we could even double the performance of 1 meg I/O from a single thread. I think we might even be able to do better than that. So, and it'd help for shared file I/O. Now, the downsides are, this is obviously kind of complicated. Luster's already pretty complicated. And it would only benefit sequential I/O. If you're doing random I/O, it would in fact be marginally harmful. You'd leave it off, but checking for it would, might be so small a harm as to be unmeasurable, but it would have no benefit. So, moving on to random I/O, which is sort of the last thing here and our least favorite. So, and it's worth mentioning when I say small random I/O, and I don't mention large random I/O, it's because for the purposes of a file system, once I/O is large, it's not really random anymore. By the time you're at 8 or 16 megabytes, most of the things the file system does are fully spooled up, and so the difference between 8 or 16 and 256 megabytes is often uninteresting. So the file system is fully spooled up. So if you're doing your IOR with random at 8 megabytes, I don't know how interesting a test that is, to be honest, and I'd expect it to look a lot like IOR sequential at 8 megabytes for most purposes. So with random I/O, and again, this is with small stuff, you can't do read-ahead. You can't batch the writes to disk because they're not in order together. Somebody will bring up ZFS, which can do some of that in some situations, but it's still not ideal. And so we do batch the writes at the network layer. So if you write 8 bytes here and 8 bytes somewhere wildly elsewhere in the file, and then repeat that a number of times, they can go in the same network RPC. And that has a huge benefit. You can sort of experiment with turning it off in certain ways, and it's very useful. But it's still not that great. And having flash on the servers helps a lot. Obviously you get that 100,000x speed up in IOPS, from flash versus spinning disk. But random I/O is still not great. So with random I/O, it's all about latency. You can't make it big. You can't cheat. You can't pile it up to do it at once. You can't do it before someone asks for it. And so you just have to do it as fast as possible. And the complexity of Lustre means it's got a relatively high per IO latency. So, like I discussed before, there's not really any silver bullets. If you look at flame graphs of what Lustre does during an IO, the answer is it does a lot of different things, and none of them are especially painful. Direct I/O is a little better than buffered I/O. You can skip a certain amount of the locking and the tracking. Basically because there is somebody there, because direct I/O is synchronous, there is somebody there to receive an error, so you don't have to work quite as hard to try to make sure that no error will happen. The last thing, and this is where we can actually do something, is network request latency. And on an HPC network, it's interesting to note that unlike, say, the internet, in fact, on an HPC network, often the majority of latency is things like waking up processes to do the network request and not the actual time on the network. HPC networks are single-digit microseconds, at least for Cray areas, and I think the better InfiniBand implementations are similar. So this is what we did. It's an old work from the former Seagates, then Xyratex, and now Cray colleagues of mine. It's a few different people did this. It's called immediate short I/O. So normally, Lustre does all transfers, all data transfers using RDMA, and what that means is you have to set it up. Basically, there's a negotiation that says, this is where the memory for this transfer lives, and now then please do the RDMA. So you end up with at least 2 round trips, and in practice, a few more for various reasons. And that's good because RDMA is nice and fast, and you can skip a lot of the handling of messages. You don't have to sort of do a formal send receive. You can just do direct memory operations, and that's fine. But at a certain point in size, which does vary a lot depending on your network and other things, the extra round trip is worse than handling a larger non-RDMA message. And so that actually leads to a pretty simple solution. You can put small I/O into the buffer in an RPC. So basically, the announce message that says, here is where the data is, says the data is inside me. And so now that message isn't 500 bytes, it's 4K plus 500 bytes. But on a lot of networks, that's still faster than setting up an RDMA. In general, it is. So what we saw is about 30% faster on reads on Cray's Aries network, which is about as low latency as HPC networks get. I don't think anything's lower. And that's to flash. And so if you had a slower network, like for example, if God forbid you're running over your sort of vanilla Ethernet and TCP, you would see a bigger benefit. I mean, particularly if you're doing some sort of long distance thing, although if you're doing that, God help you. But, you know, and this is, again, this is to flash and to spinning disk. It was in the noise because spinning disks are so much slower on these small I/O to begin with. It was too small to measure on writes, unfortunately. So we've got it, it's helpful, but like I said, it's not that great. Small writes take a lot longer than small reads. So we're actually almost done. So a little summary, small I/O is really hard. It's hard for any kind of file system. Everybody's performance drops precipitously as size decays. Nobody likes it. And it's also worth noting, people think flash solves the small I/O problem. Every flash drive that you can buy quotes an IOPS number, and it quotes a bandwidth number. You can't have those at the same time. They want you to think they can. But that bandwidth number is actually with like 4 meg or 8 meg IOs or something, and that IOPS number is with whatever the natural minimum size on your flash device is, which might be 4K or whatever, you know. And so even flash goes a lot faster if you can do larger IO. And that's, again, part of why it's so interesting to take the time to do this write aggregation and read ahead on the clients. So Lustre 2.11 contains some significant improvements in this area. There's other stuff that could be done. It's a sort of summary of what we did. Got a little bit more about what we might do. For reasons that I could get into in detail if anyone wanted to hear about it, you can't use tiny writes when you're appending to a file. Appending is surprisingly difficult in a parallel file system because of the details of the POSIX semantics. And I want to stress that when I say appending, so people think about this, I don't mean seeking to the end of the file and writing there. I mean O-append. These specific semantics of POSIX O-append are very difficult for parallel file systems. So as we're noting as well, just as a general tip, if you were using O-append and you don't need to be, try to stop. If you can write your application in a way maybe where it would seek to the end of the file and write there, and if that's okay, there are a not insignificant number of things that might benefit from that. It's just, in general, append is not great. Write containers, like we talked about. And then asynchronous read-ahead, which would be really nice to finally get nailed down. That's been floating in the air for the first work from DDN, I think is maybe 2 years ago. And you know, just competing patches and et cetera, and different debates over what improves which workload. It'd be great to get that pinned down. Finally, about random writes, when I brought this up at LAD last year, Andreas suggested that maybe since we do spend most of the time journaling, even on Flash, for a 4K write, you spend more time journaling than you do writing to the actual file. There's not a lot of fat to be squeezed out of the journaling code. Trust me, it's already had attention. You know, people know journaling is a performance-sensitive thing, but maybe you could skip it. And maybe there's some hay to be made there. It's sort of a, it's an interesting idea. It's not trivial, not totally trivial to implement, and it would require user buy-in and specific awareness of maybe what the dangers were. And so, like so many things, if you can't do it all the time, is it worth doing if you can only do it part of the time? So, Like I said, this is all stuff that is in 2.11, with the exception of what's on this slide here. So, do we have any questions?
Probably got time for one, so we can give Hugo enough time. So make it a good one. Or no one.
Small random I/O is all about latency. Can we improve the latency of it by using the network request scheduler? Sorry.
Not from the perspective of what I'm thinking about. So what I'm thinking about is the sort of the software latency on the client. You certainly could in a contended system. So that's one thing that's worth talking about. Is everything I said today is basically from the perspective of a single client in not necessarily an uncontended system, but in a system where I'm sort of disregarding the effects of contention. So there's, as always with Lustre, there's sort of worlds of other similar sounding and potentially linked problems that are not discussed here. That is one of them.